Alright, so this is the last video of the semester. We're going to go over one of the applications for diagonalization of a matrix, forming powers and polynomials of matrices. This is something that you see a lot of use of in physics, in chemistry, a lot of computational problems, a lot of things like dynamical systems, predator-prey problems, population evolution, any sort of discrete dynamical system where things evolve in stages. A lot of these can be modeled as kind of, you start with a vector describing an initial state, and then to get to the next stage you multiply by some matrix A, and then to get to the next stage you multiply by A again. And so if you want to know what's going on after, say, 10 generations, well, then you need to multiply by A to the 10th, right? After 100 generations, A to the 100th. Well, matrix multiplication it's not too bad when you got to do one multiplication, but it's computationally intensive. Large powers of matrices is computationally difficult. And so if you can find ways to compute powers efficiently, then you're in a much better shape to sort of look at some of these problems, look at some of these models where this comes into play. Okay. So in the last video we had this matrix A, and we found that there were two eigenvalues. We said the lambda equals 2 eigenvalue was repeated. It showed up twice. Lambda 2 equals 3, that eigenvalue showed up only once. So with a bit of work you can compute the eigenvectors for these eigenvalues. There they are. Okay, so I have this this vector and this vector for the first eigenvalue, this guy for the second, and so the way you diagonalize, the process of diagonalizing your matrix, is that you take those three vectors, you arrange them as the columns of a matrix. Because those vectors are independent, we're guaranteed that this matrix will be invertible, and so we can go ahead, we can compute the inverse. There it is. We get lucky this time, the inverse actually has integer entries. And if we do P inverse times A times P, we get our diagonal matrix D. 2, 0, 0, 0, 2, 0, 0, 0, 3. So 2, 2, 3, we see the eigenvalues sitting on the diagonal. Okay, so what can we do with this? Well, one of the things we can do with this is we can use this to compute large powers of A. Okay, so we want to calculate, so I'm doing A to the 7th, but maybe, like we said, we might want to do like A to 100 or something, right? How do we calculate this thing? Well, we said that we found this matrix P, so that P inverse times A times P was equal to this diagonal matrix D. Rearranging, we can write like that. So if I wanted A to the 7th, well, that's going to be P D P inverse to the 7th, right? So that looks like P D P inverse times P D P inverse times, well, okay, there are 7 of them. I'm not going to write them all, right? So we do that 7 times, and you'll notice that, well, here you've got a P inverse next to a P. I can cancel those, right? Because P inverse times P gives me the identity. Multiplying by the identity does nothing, right? This next P inverse cancels with the next P, and so on. There's a P inverse here that cancels with that P, and what I'm left with is P times, well, there's going to be, all this left in the middle is D. D, 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 there's 7 of them. D to the 7th times P inverse. Okay. Well, that's easy enough because I know, here's P, we've got our P, 105. D to the 7th, sure. When you multiply two diagonal matrices together, all you have to do is multiply the diagonal entries. So if I multiply a diagonal matrix by itself 7 times, I'm just taking the diagonal entries and raising them to that power. So D to the 7th looks like 2 to the 7th, 0, 0, 0. 2 to the 7th, 0, 0, 3 to the 7th. Okay. Then I do my P inverse. Where is it? There it is. 510 minus 4. 2, 5 minus 2. and minus 1, minus 2, and 1. Okay, and then I just have to multiply that out. I'll leave that for you guys to do. I'm not going to do the multiplication, but you can multiply everything out if you really want to. I'm not going to bother. I'm also not going to calculate 2 to the 7th, or 3 to the 7th. We'll just leave those powers alone. But the remaining matrix multiplication is straightforward, right? I've got to do 3 matrix multiplications instead of 7, so I've saved myself a bit of time, right? Of course, I still had to do all the work to diagonalize the matrix, but it's still we're still probably a little bit better off here. And if I was doing a to the 10th, a to the 20th, a to the 100th, then I'm definitely better off doing it this way. Okay. Now, once you know how to do powers, you can do polynomials. Okay, so the way you define the polynomial of a matrix, right, is you just plug a in for x. The only one where you've got to kind of deal with is the constant term. So the way p of a is defined is it's an times a to the n, an minus 1, a to the n minus 1. So on down to a1 times a, and for the a0 you need to have a matrix here. You can't just have a number, but that's okay. We multiply by the identity. Okay. Now, if a is diagonalizable, then as we did on the last slide, we know that we can write a as p d p inverse. So you can plug that in everywhere. an p d p inverse to the n. Let me skip the next term just to save some space, down to p d p inverse plus a naught times I. Okay. But I know that p times d times p inverse to the n, I can write that as a to the n, and then p, and then d to the n, and then p inverse. Okay, down to a1 p d p inverse plus a naught times I. And here's the trick. I can bring this p, I can move the p past the scalar, I can bring the scalar inside on each one of these terms, right? And I can, matrix multiplication is distributive, which means I can factor the p out on the left, I can factor the p inverse out on the right, and just to make things kind of crystal clear, I can write the identity as p times p inverse. Or if you like, p times the identity times p inverse. So if I pull the p out on the left, I've got an d to the n, okay, down to a1 times d plus a naught times I times p inverse. And we can go one step further. I know what each one of these d to the k's looks like. Okay, I know that d to the power k, where k is anywhere from 1 to n, it looks like lambda 1 to the k, and then lambda 2 to the k, down to lambda n to the k. It's diagonal, with powers of lambda down the diagonal. And so if you kind of do things term by term, it's quite a remarkable thing that happens. You get p times a diagonal matrix where the diagonal entries are your polynomial applied to lambda 1, polynomial applied to lambda 2, down to the polynomial applied to lambda n, zeros, zeros, everything else is a 0, 0. Okay, you get a diagonal matrix whose diagonal entries are just the polynomial evaluated on each of the eigenvalues, with this matrix p on one side and p inverse on the left, right? So a polynomial of a matrix, not so bad. You just have to actually calculate the values of the polynomial on each eigenvalue, which is a simple numerical computation, right? Plugging a number into a polynomial, we can all handle that. And then you have to do a matrix multiplication at the end. So this is a hugely valuable observation. Gives you some major time savings, and there are, again, quite a number of problems where computing polynomials of a matrix is a necessary procedure that you have to perform. Okay, so let's do one example. Okay, I don't know if we've worked out the eigenvalues for this guy, so we've got to do some work first. We've got to diagonalize this guy. Right? This is not the one that we saw before, is it? I don't think it is. Let me just check. This was not the matrix we started with, was it? Ah, it was. Okay. So we've got our, let's see, we got to remember things here. So eigenvalues are 2 repeated twice, 3 shows up once, and we've got these 3 eigenvectors, 1, 0, 1, minus 2, 1, 0, 0, 2, 5. So here's our matrix P. Okay. So let's do this. Okay. So we had our matrix P was 1, 0, 1. Okay. I'm bad at remembering these guys. Minus 2, 1, 0, and 0, 2, 5. Minus 2, 1, 0, 0, 2, 5. Let's keep track of that for now. Lambda 1 is equal to 2. That one shows up twice. Lambda 2 is equal to 3. Okay. So we want to calculate P of A. And so the previous slide says, well, that's the same thing as P times P of D times P inverse. All right, and P of D, I can calculate that. I have to calculate P of 2. Okay, so P of 2 is going to be 2. So 2 cubed is 8 times 2 is 16. 16 minus 12 plus 8 plus 1 is 13. Okay, P of 3, we're looking at, so 3 cubed is 27 times 2 is 54, minus 27 plus 12 plus 1. So 27 plus 12 is 39 plus 1 is 40. So what we get is, so let's just kind of put that on the side. We get P times the matrix 13, 0, 0, 0, 13, 0, 0, 0, 40 times P inverse. Do we want to finish this off? If we want to finish this off, let's go and make a note of what was P inverse. There it is. So we've got 5, 10, minus 4, 2, 5, minus 2, minus 1, minus 2, 1. Let's copy that down at the end. Okay. So what we get is 1 minus 2, 0, 0, 1, 2, 1, 0, 5, 13, 0, 0, 0, 13, 0, 0, 40. The numbers are going to get a little bit big on us here, but let's try it. So we had 5, 10, minus 4. I wrote them down on paper this time. 2, 5, minus 2, minus 1, minus 2, 1. Okay. So what are we going to get? We're going to get 1 minus 2, 0, 0, 1, 2, 1, 0, 5 times. So the first row gets multiplied, so I do row 1 times column 1, 2, 3. I'm multiplying by 13, so 65, 130, and minus 52. Next row also gets multiplied by 13, 26, 65, minus 26. And then the last row gets multiplied by 40, minus 40, minus 80, 40. And then we carry out that last bit. It's going to be that's a little bit of a mess, isn't it? 65 minus 52 is 13. 130. Oh, that's a 0. Then we're going to get, let's see, minus 52. I get 0. Oh, this could be convenient. I don't think that's going to work out that well for me. Let's try it. Let's see if this works. There we go. Now we get some action. Next row. 26 minus 40. That's minus 14. Then 65 minus 160. That's what? Minus 95. And then minus 26 plus 80, 54. And then we got to do the last row. The last row, we've got some work here. 65 minus 200, minus 135. Oh geez, the next one's going to be ridiculous. 130 minus 400. Okay, minus 370. And then finally minus 52 plus 200. That's 148. Okay. All right. So that's not so bad. That's certainly going to be a lot easier than doing a cubed, a squared, a, plugging everything directly into the polynomial. This once you've diagonalized, this is much less work. Okay. That is it for the videos for this course. That's the last example that we wanted to do. So all that's left is to tackle some problems in class.